Hello, everybody. This is me going through the final exam review problems. I'm doing this a little bit differently from the last video I made for the test 3 review. It took a long time to do it that way. This time what I've done is I've just worked the problems out. I'm going to talk you through them. Okay, so of course you can come to my office hours. On Monday, I'll be there from 3:30 to 4:30. And Wednesday, I'll be there from 9:30 a.m. till 10:30 a.m. You can talk to me about any of these that you want to talk about. Okay, so let's go ahead and jump ahead to the first problem. So let me just kind of walk you through what I did on these. So the first one says to prove that the set of all singular, and singular means that the determinant is 0. So singular 3x3 matrices is not a vector space. So to prove that something's not true is different from proving that things are true, first of all. To prove that something's not true, all you have to do is provide an example of where it's not true, and then it's not true in general. Proving things are true in general has to prove every case. So you have to prove things in general with a general case. But to prove something's not true, you just have to provide a counterexample. So that's what's happening here. It's something that the singular matrices are not a vector space. First thing I thought about was that if it's not a vector space, then it's probably not closed under multiplication, so or addition, I should say. So what I did was I came up with two vectors that have determinants of 0. And you remember that the determinant of a diagonal matrix is just the product of the entries on the main diagonal. So this determinant is 0. It's 1 times 1 times 0. And this determinant is 0, 0 times 0 times 1. So both determinants are 0. But when you add them together, you get 1, 1, 1. And we can see the determinant of this is 1. So adding two singular matrices together results in a matrix that's not singular, so they are not closed under addition. And that's all you really need to say on this one. I'll be posting this PDF as soon as this is over. Okay. Next one, determining whether a set is a subspace. There's a lot of ways to do this, but something I like to do is try to show that a set is a spanning set. So if you look at this x plus y, y, the x's, x can be brought into the first vector, x times 1 with nothing else in the next two components. Okay, the y's in the second, third, and fourth components, y, can go in the second vector. Second one has to be multiplied by y, first by x. If you combine these, you get this. And you can see that vectors of this form are just the span of 1, 1, 0, 0 and 0, 1, 1, 1. So this set is spanned by these two vectors. And we know that the span of any set of vectors is a subspace of the vector space that they are in. So these vectors are in R4, and the span will be a subspace of R4. And this span is just the combinations of these two vectors which add up to this, which is exactly the set we're talking about. So that's number 6. Okay, so next, number 9 looks a little bit more involved. So first of all, it says in part A to explain what it means for a set of vectors to be linearly independent. So this is just the definition, and there's lots of theorems about linear independence, but I just started by giving the definitions. The sum of the set of vectors is linearly independent if the only solution to C1v1 plus C2v2 dot 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 plus CNVN equals 0 is that all the scalars have to be 0, which is a trivial solution. Okay, so all I'm doing now in part B is showing that these vectors down here have to show whether they're independent or dependent. So I do exactly what I said in the definition. C1 times the first plus C2 times the second, and so on. set them up to be equal to 0, and then I show what the system of equation is that this implies. That you can see the first equation, C1 times 1 plus no C2, C2 times 0, plus 1 times C3, plus 3C4. That has to be the first component here, which is 0, and that makes the first equation. Second components make the second equation, and so on. Now, what I did was I found the coefficient matrix of this down here, and which just happens to be these vectors stacked in rows. Since it's 4 by 4, I went ahead and took the determinant and found that the determinant was 22, not 0. And when the determinant is not 0, that means that the only solution that can exist to this linear system is a trivial solution. If the determinant was 0, then one of these rows would 0 out and you would get a non-trivial solution. So with the determinant not equal to 0, we know only the trivial solution exists, so the vectors are linearly independent. And that's all you have to do on that one. Okay, now let's go to number 12 here. Here it says to find the coordinates of the vector v with respect to the basis b for the vector 1, 2, -3, where b is this 0, 1, 1, 1, 1, 1, and 1, 0, 1. So I just take this 1, 2, -3, and I set it to be a linear combination of the vectors from b. Solve the system of equations that's implied by that. First equation is 0a plus b plus c equals this first entry, which is a 1. And so that's the first equation there. And then a plus b plus 0c is the second element, which is 2. And so that's the second equation over here. Anyway, so you get this system of equations, and you take a little time to solve for a, b, and c. And those are the coordinates of the vector relative to this basis. So you know the A, B, and C are the entries A, B, and C in the representation of B relative to B. So the A, B, and C are -4, 6, and -5, and so that's the vector, okay, represented using B coordinates. Okay. Next one. Now transition matrix, we've done these enough. You want to change from basis B to B prime, and you just need to remember to put, I used a beta, but you use B prime first and then B, and do a row reduction until you get an identity matrix. And then this thing over here is called P inverse, which is the transition matrix we're looking at, that to transform V with a beta prime, from V with a beta representation, you have to multiply P inverse times that vector to get the representation of B relative to beta prime. Okay, so that's the process. Pretty straightforward. Okay, now number 15. This one asks for a very simple thing, just to evaluate an inner product. So the inner product of x squared and x plus 2 on the interval from 0 to 1, you just multiply the two functions and integrate, which I did, and I got 11/12. If anybody was to ask me a follow-up question, it might be, are these vectors orthogonal, or are these functions orthogonal on this interval? And I would say no, because the inner product is not 0. Okay, can't think of anything else to say about that one. Thank goodness I don't have to do Gram-Schmidt on that. That's I could say that. Okay, next one. Oh, I just said the word Gram-Schmidt. Here we go. So this one says to apply the Gram-Schmidt process. Now this says orthonormalization, so we have to make these unit vectors to transform the set of vectors into an orthonormal basis. This one's pretty nice, actually. 2, 0, 0, 1, 1, 1, 0, 1, 2. So I call those V1, V2, and V3, and then V1 is always W1, and W2 is V2, but you have to subtract out the W1 component of V2, so that it will be orthogonal to W1. And then you do it again for W3, you make it V3, but then you have to subtract out the W1 component of V3 here and the W2 component of V3 so that the result will be both orthogonal to W2 and to W1. So you get these three vectors, and you guys remember, anytime I get fractions in this, I'll always put a scalar in here to clear those fractions. I see the denominators here of a 2. This one's going to reduce to a 2. So I multiply by 2, and I just get 0, -1, 1. No fractions. That makes me happiest. The other one had a 2/4. It was multiplied by a 2. That one clears by itself. So I didn't need to multiply this one by any scalar. So I get the three vectors, 2, 0, 0, 0, 1, 1, and 0, -1, 1. These have to be made unit vectors. So we divide them by its length. 2, 0, 0 as a unit vector just gets scaled down to 1, 0, 0. That's kind of obvious. The next vector, 0, 1, 1, has a length of the square root of 2, so we just divide that. The next one also has a length of the square root of 2, we just divide that. And these are orthonormal. The dot products of any two will be 0, but the dot product of 1 with itself will be 1 because these are unit vectors. Okay, so that's 16. Let's go to the next. This one's kind of, I didn't really like the way the graphics worked out on this, but this one they're asking to graph U and V and the projection onto V of U. So the projection onto V of U is just this formula here, U dot V over V dot V times V. And that's what I'm subtracting out when I do Gram-Schmidt up here. All of these, when you subtract out, the W1 component of V3, that's just the projection of V3 onto W1. Okay, and so we're just subtracting out projections when we're doing Gram-Schmidt. And so this one is really hard to see because U and V already look kind of orthogonal, but they're not. Turns out that if you take the projection onto V of U, you get this little teeny vector, -3/13, 2/13, which is parallel to -3, 2, which is V. Okay, and we know this is a projection onto V, so the projection has to be parallel to V, but it's a little teeny short thing. And if you were to take U and subtract this projection, you'd get this gray vector here, which is orthogonal to V. And that's the idea of Gram-Schmidt. Anyway, moving on to the next one. Okay, now this one, it's hard to remember all these terms. So, and I hate the notations that they use in the book, and they call these the 4 fundamental subspaces. And to be really honest, this N of A, R of A, N of A transpose, and R of A transpose is just obnoxious notation here. The 4 subspaces are just the null space and the column space of both A and A transpose. They use R of A because that's the same as the range of the transformation A of T of X equals A times X. So the range is the same as the column space. And it's just sort of unfortunate that they use these bizarre notations, but there they are. So you can see I'm just kind of pounding through doing this twice. The null space is always found by solving, AX equals 0. Okay, so that ends up just being A attached to a 0 vector that after row ops, you're going to have to row reduce. And I end up with a non-trivial solution because X3 here does not have a leading 1 in its column. It has a 1, but it's not a leading one. So X3 is the one that gets to be an independent parameter T. And so the other variables are expressed in terms of T. And so the null space of A is just the span of this one vector. And so that's pretty straightforward. The column, there's a couple different ways to find a basis for the column space of A. There's a more advanced method that the book talks about that's actually less work, but it's much harder to comprehend. So I tend to go with the easiest approach. Okay, so the easiest way to find the range of A is, first of all, to remember that's the same thing as the column space of A. And because we don't do column operations on matrices, just because we don't, we do row operations, it's easiest to just say, well, doing column operations on A is the same thing as doing row operations on A transpose. So basically, we just look at A transpose, which is this guy down here, and I row reduce it here. And in the end, I end up with the simple basis 1, 0, 0, 0, 1, 0, 0, 0, 1, which is just a basis for R3. And those non-zero rows should be turned back into columns again, because you are doing a column space, but these are going to be independent vectors that will span the column space. Okay. Now we do the same thing with A transpose here. So first we have to find the null space of A transpose, which is simple enough. We're solving A transpose times X equals 0. And so I take A transpose and I attach a 0 vector. I row reduce it. Now I've already row reduced A transpose. So this is going to be super easy. X1, X2, and X3 all have to be 0. So the null space of A transpose is just a 0 vector. Okay. Finally, the row space, the range of A transpose is the same thing as the column space of A transpose, which is the row space of A. And we've already row reduced A. So if you go back to the row reduced form of A and just get the non-zero rows, I wrote them as column vectors and maybe I shouldn't have, I don't know. But I'm just going to back to the original matrix A. These rows here, 1, 0, 0, 0, 0, 1, 1, 0, and 0, 0, 0, 1, those are a basis for the row space of A, which is the same as the column space of A transpose, and that's these vectors. I wrote them as columns, but because it's a column space of A transpose, whatever. These are just the rows of A when we row reduced it. So there's a lot to remember here, but there's actually not that much work, and some of it was redundant. Okay, going to the next problem. This one is gonna be another nullity or a null space. So when you take an orthogonal complement of a set, you're looking for vector where the dot products with these two vectors, I want all vectors such that the dot product with both of these is going to come out to be 0. Okay, so let's see here. What did I say? We need a vector xyz whose dot product with both of the above is 0. So when I dot 1, 0, 1, this guy with xyz, I need to get 0. And negative 1, 1, 0 with xyz needs to come out to be 0. So hang on. So this ends up being, x plus 0y plus z, which is essentially what I coded in the first row of this. And the next one's negative 1, 1, 0 dotted with xyz, and you see this as the second row here. So basically, I just combined these two equations into one matrix equation, and it's got to be 0 because this row has to be orthogonal to xyz, and the second row has to be orthogonal with xyz, which means both those dot products are going to be 0. And look, you're just finding the null space of this matrix here. So here I go. I'm taking that matrix, and I'm augmenting a 0 vector to it, just as because we're just finding a null space. So you do the row reduction, you get this. Looks like Z does not have a leading 1. So Z gets to be T, and X and Y are expressed in terms of T. And so the null space is just any multiple of -1, -1, 0, which is the orthogonal complement of S, which we call S perp. It's the span of this one vector. Okay. So there's 19, all done. Here comes 21. This one's the least squares. Curve fit, super easy if you take the time to just sort of pay attention. I will put this on the final because these are important. You can fit any curve to any linear combination of functions can be fit to any collection of data points using this method. So we've been fitting lines to these data points, but you could fit quadratics to data points as well. And it's the same technique. So this is a very powerful technique, much more powerful than what we usually teach in statistics, which is only good for line fitting. So this is a pretty slick algorithm. So you say mx plus b equals y, which it's nice to have the y on the right. And we're just going to plug in the x's and the y's for all the data points into this thing, which is the equation of the line. So I did that here. I wrote it in matrix form, right? This one says m plus b is 1, and which is basically what's happening. 1m plus 1b equals the first entry, which is a 1, and then it's 2m plus 1b equals 0, which is the second equation. And again, I'm getting these equations just by plugging all 3 points into the equation of a line. Okay, so you end up with just a vector equation. A matrix times a vector equals another vector. And it has no solution because these 3 points don't line up. If you graph them, they don't lie in a straight line. And yet we're trying to find the closest line to them. So the least square solutions to AX equals B is found by left multiplying by A transpose both sides. Okay, so I got an A transpose multiplying both sides. You see A transpose here and A transpose here. The same vectors are in place otherwise. And it ends up that you end up with a smaller system of equations when you do this that you can row reduce. And here you see that m is this -20 over 13, and b is the 36 over 13. And so it's y equals mx plus b, and that's the least square solution. It's super simple, and it's a really neat algorithm for doing that. Okay, now on number 23, this one doesn't really look like they want a proof. And so what they say is let S1 and S2 be 2-dimensional subspaces of R3. So a 2-dimensional subspace of R3 has to be a plane. Remember, all subspaces must contain 0. So that's another way of saying that these planes pass through, or they contain the origin, okay? All subspaces of a vector space have to contain the 0 vector. So both of these planes have to contain the origin, okay? And so the question is, can 2 planes intersect only at the origin, just 0, 0, 0 here? And I think the answer is no. So here's how I see it. Either the 2 planes are the same plane, okay? And if they are the same plane, the intersection is 2-dimensional. So it would have a basis of 2 linearly independent vectors and basically just be a normal plane. That's a lot more than just 0, 0, 0. So in that case, the answer is no. If they're the same plane, no. Now, if they're different planes that both contain the origin, then if they're not the same plane, then 2 different planes will intersect in a line. So that's what I've drawn with this green vector, or this green line. This green line is the intersection of 2 planes that both contain the origin down here, okay? So if they intersect in a line, then the intersection is one-dimensional, which has to be spanned by a non-zero vector. 0, 0, 0 is zero-dimensional and is spanned by nothing. Nothing. You don't need a vector to span 0, 0, 0. Okay, it's just, it doesn't go anywhere. So the intersection is either two-dimensional or one-dimensional, and in either case, that's a lot bigger than just 0, 0, 0, which is zero-dimensional. Okay, so that's sort of my argument here. I'll just leave that up for a second. So I said in either case, the dimensionality of the intersection is different from that of the zero vector, which has dimension 0. Okay, again, the intersection is either two-dimensional when it's the same plane or one-dimensional when they're different planes. Okay. Next. Well, this one was hard. To me, it was just so, I hate proving things that are super obvious. And I couldn't think that we don't have a theorem that just allows you to knock this one out of the park real quick. We do know that every basis of vectors for a vector space always has the same number of vectors. And we did have a proof for that. So the problem I had was, well, they don't say that this set of less than n vectors, they don't say that it's linearly independent. So, you know, if the set is independent, then it spans V. Sorry, if it's independent and spans V, then the dimension is the number of vectors in this set, which I'm calling S. And so if S has less than n vectors, then the dimension of V would be less than n, but it says that the dimension is n, so that's not possible. This set cannot be independent and span V. Anyway, this is how I did it. I said, suppose S has less than n vectors and that span of S is equal to V. Okay, first of all, if S is linearly dependent, we can remove vectors that are dependent without affecting the span. Do this until the set is linearly independent. Okay, so now I'm saying the set is independent. So now, and it still spans V. Okay, so I said now we have a set that I called U with K vectors, where K is less than n, that spans V. So the dimension of V is K, and K is less than n. Remember, the number of vectors in the basis has to be, the number of vectors in the basis is equal to the dimension of the space. So I've got one set with K vectors, so the dimension is K, and it's linearly independent. But up here it says the dimension is n, so there's a contradiction here. So dimension of V is n, and this is impossible. So U cannot span V. U is the set of K vectors. But the span of U is equal to the span of S. So also S cannot span V, which I believe that's what they're asking me to show here. Okay, to the next one. Okay, so this one, I think there's a lot of redundancy with kernel and nullity and so on and so forth. But let's look at number 6. I'm not going to do so many redundant questions on the final. There's a lot of stuff I could have taken out of this review. But anyway, let T map from R4 into R2 be the linear transformation divided by T of V equals A times V, where A is this 2x4 matrix. It says find a basis for the kernel of T and the range of T, then determine the rank and the nullity. So you guys have seen problems like that before. So for the kernel, that's the same thing as finding the null space of the matrix A. So I'm setting AX equal to 0, attaching a 0 to A to solve a system of equations. This thing is already basically in reduced row echelon form. At least I have to multiply the second row by -1, and then it is in reduced row echelon form. So that's super easy. I end up with V3 and V4 not having leading ones in their columns. So V3 and V4 get to be independent. So I made V3S and V4T. V1 and V2 are in terms of S and T. So here's my vector, negative S, negative T, ST, which I split up into two independent vectors so that the kernel is spanned by those two vectors. Okay, that's two-dimensional, so the nullity will be 2. Now the range of T, as you probably remember, is the column space of A. And so I like to find a basis for the column space by row reducing A transpose. By doing that, reducing the rows of A transpose, I'm reducing the columns of A. And I end up with 1, 0, 0, 1 that I will transpose here, and those become the basis for the column space of A, which is the range of T. Okay, and then finally, the rank is the dimension of the range. And so the range was two-dimensional with a basis of two vectors. The nullity was the dimension of the kernel of T, and the kernel was two-dimensional. So the rank and the nullity are both 2. When you add those up, you get 4, which is the dimension of the space we're mapping from R4. So those have to add up to 4. Okay, so that's 6. And then on number 9, there was almost nothing to do here. There it is. I like to write my transformations from Rm into Rn as column vectors like this. And once you write them as column vectors like this, it's very easy to turn them into a matrix multiplication. And this thing that I've got here is the standard matrix. For T. I know there are other ways to do it, but that's the way I normally do it, and I think it's fastest. Okay, now this one is easier than it sounds. It says, to find the matrix of the linear transformation T of xy equals y 2x x plus y relative to the bases B, which is 1, 1, comma, 1, 0 for R2, and B prime, which is 1, 0, 0, comma, 1, 1, 0, comma, and 1, 1, 1 for R3. Use this matrix to find the image of the vector 0, 1. All right, so first of all, I need to know the matrix for A relative to B. And notice B, they give the transformation relative to B already here. So this, when I describe the transformation this way and then write it as a matrix product, this is already relative to B. So, or beta as I say here. So A is the standard matrix of T relative to B because that is how it was given. Okay. Now, if I do the transformation and apply it to the point 0, 1, then I just take this matrix here and I multiply it, my A matrix, and I multiply it by 0, 1. Okay. Now, when I multiply this out, you can see I get 0 times 0 plus 1 times 1, which is 1. All right. And then 2 times 0 plus 0 times 1, which is 0, and so on. So I get this matrix down here. Okay. Now it says that this is relative to beta prime because this transformation is mapping from beta in R2 to R3 relative to beta prime. So this is already set up. This is already T of 0, 1 relative to beta prime. So this is 1, 0, 1. So there's nothing more to do. You just multiply the matrix times the first vector relative to its basis, and you get the next vector relative to the basis for R3. I wanted to show you how to express this output relative to the standard basis. just recognizing that relative to beta prime, you get 1, 0, 1, and those are the scalars 1, 0, 1 for the vectors in beta prime 1, 0, 0 here, 1, 1, 0 here, and 1, 1, 1 here, okay? So the third one anyway. And when you add this all up, you get 2, 1, 1. Now that's the representation of the same vector, but it's relative to the standard basis. So the standard basis is the old IJK 1, 0, 0, 0, 1, 0, and 0, 0, 1, like that. Okay, so this was not, they didn't ask for this in the problem. Okay. All right, let's go to the next one. This one, oh God. Ooh, all right, so this one is another one with a change of basis, but this is straight from section 6.4. We've got B here is the standard basis, okay, 1, 0, and 0, 1, but B prime is 1, 1, 1, 2. Both of these are bases for R2. Now I have the matrix, I need to find the matrix A for this transformation from R2 into R2. The transformation is x minus 2y, comma, x plus 4y. So I did that first here, writing it as a column vector, x minus 2y, x plus 4y. The coefficients are 1, negative 2, 1, 4, that you can just see here for x and y. And if you multiply it by the column vector xy, you get what they started with. So the matrix for the transformation relative to B is just this 1, negative 2, 1, 4 matrix. Okay, so that's the standard matrix for the transformation. Okay, now we also need to figure out, and that's question A. Okay, just the standard matrix. And then in B, they want the transition matrix that goes from beta prime to beta. So we've done this before. You set up a matrix that augments beta prime coordinates first to beta. You do these in columns. So the first column is the first vector in the basis beta prime. And the second column is the second vector for beta prime. And then the third column is the first vector for beta, and the fourth column is the second vector for beta. Okay, so you want to reduce this to the identity matrix, and on the right-hand side of the augmented matrix, you end up with P inverse, which is the transition matrix. So you can see it was actually a really easy row reduce to come up with an identity matrix in the first two columns. And then the second matrix is our P inverse transition matrix. And while I was at it, I found out what P was because I knew I'd need it. Okay. Now, just to remind you of the diagram from section 6.4, if you're trying to transition or to transform vectors relative to beta prime under the same linear transformation, the matrix for the transformation relative to beta prime is P inverse AP. Okay, we just computed P inverse and P, and A was the initial matrix that we've got down here. So to do the transformation relative to beta prime, we need to do this transition. Okay, so when they're asking for that in part C, find A prime of T relative to the basis beta prime, they're asking you to do what's here in part C. So all I'm doing here is I'm multiplying P inverse times A times P, and I did it twice and I made a mistake twice. The third time I did it, after a lot of frustration, this is what I got, and that's the one that checks out. Okay, so this is A prime, it's just P inverse AP. And now they're asking in D to find T of V relative to beta prime, where they give you V relative to beta prime. Okay, so it's nothing more than understanding that to transform a vector relative to a given basis like beta prime, you have to have you have to know the matrix, the standard matrix relative to that basis, beta prime, which we call A prime, and you just multiply by the vector V relative to beta prime, multiply it out, and it comes out to be 9, -6. Now, this I wanted to express in terms of the standard basis. So this is relative to S. Just for you to see, this comes out to be 3, -3. Okay. And what I'm doing is I'm taking the two coefficients, 9 and -6, and multiplying by the first vector in beta prime minus 6 times the second vector in beta prime, and I get this 3, -3. Now, if I want to take that vector V relative to beta prime and express it to beta, relative to beta, you might think about this diagram up here. We were starting with vectors V relative to beta prime, and we used a transition matrix P to get that vector relative to beta, the different basis. Okay, so you take this vector, you multiply it by P, and you get V relative to beta. So that's what happens next. I think we're on D. Verify your answer by finding V relative to beta here, and then T of V relative to beta. So we're just going to do this new transformation. So as I said, V relative to beta is P times V relative to beta. That should not have a prime there. So it's fixed. So P was this up here, the 1, 1, 1, 2. So I've got that down here. And then V, oh no, that was a prime. This is correct. I'm converting from beta prime to beta. So I do P times V relative to beta prime. So here's my P. This is V relative to beta prime that was given earlier somewhere up here, I guess. And you get 1, -1. And then if I want to transform that vector relative to beta, I go back to my original matrix and multiply by V relative to beta. So my original matrix was 1, -2, 1, 4. And V relative to beta was this guy up here. And when you multiply it out, you get 3, -3, which is this one over here. Okay. So that's that. Okay, so going on. Number 19. Now we're getting into the eigenvalues and the eigenvectors. Oy, this got old. Okay, so first of all, to find an eigenvalue, you need to create a characteristic polynomial. That starts by computing lambda I minus the matrix A. So A is the given matrix here. So you do lambda I minus A, which again puts lambdas on the main diagonal here and here, but then changes all the signs of the numbers in A. So you have a -7, a -2, a +2, and a -3. So it's a lambda -7, -2, +2, lambda -3. And then you take the determinant of this, and it should factor to something nice. This polynomial you get is called the characteristic polynomial, and the solutions, once it's set equal to 0, the solutions are the eigenvalues. Normally you get 2 if it's a 2 by 2 matrix. Here we only got 1 with a multiplicity of 2, which means the matrix is going to be, it turns out the matrix is defective because you only get 1 eigenvalue out of that, even though it has a multiplicity of 2. So that's not great. I'll mention that in a second down below. So I'll go ahead and add it. Since we only get 1 linearly independent vector, I should say eigenvector, from an eigenvalue of multiplicity 2, A is defective. Defective matrices cannot be diagonalized. Okay. Anyway, so once you find that lambda equals 5 here, you're going to go to that lambda I minus A and join a 0 vector to it and substitute your lambda value in. So my lambda value was 5. And when I put in 5 minus 7 here, I get -2. And then there's a -2, a -2, and a 5 minus 3, which is a +2. It's easy to see that this matrix row reduces to this with just a 1, 1, 0, and then a row of zeros, which means that the first entry is the negative of the second one. So V1 is the negative of V2. But V2 gets to be anything. V2 is T. V1 is -T. So our vector is -TT, which is T times -1, 1. And usually I like to pick a value for T that has no fractions in this. So if T is 1, my eigenvector is -1, 1. And that's all we have to do. But I'm making it a point to note this matrix was defective. And the defective matrices cannot be diagonalized. Off to the next one. Bigger. Same instructions, but this one's a 3 by 3. You want to be just real careful. Factor when you can rather than multiply, as I've told you, when you compute the characteristic polynomial. But regardless, you start by finding out, given the given matrix is A, lambda I minus A, you change all the signs of all the numbers in A and then put lambdas down the main diagonal, okay? And then you get to take a determinant of this, which worked out real nice because there are some zeros. I just expanded along the first column. And so you get these 2 zeros, and it's actually a super easy determinant, and it factors this way. You get lambda times lambda minus 1 times lambda minus 2, which is 0. So the eigenvalues are 0, 1, and 2, just like that. And so then for each lambda is 0, 1, or 2, you're going to substitute the lambda in for the matrix lambda I minus A, and attach a 0 vector to it and row reduce to solve for the scalars V1, V2, and V3, which are sort of my column headers here. There should be an infinite number of solutions every time you do this. So on this one, I got V3 without a leading 1 here. So V3 is the arbitrary one. V1 and V2 were both -1/3 times V3, so -1/3 T. And then because I don't like fractions, I choose T is 3 down here. And so my eigenvector has just whole numbers in it, okay? And do the same thing for lambda equals 1. This one was really simple, but this one's weird because it's the V1 column that doesn't have a leading 1. So V1 gets to be T, and V2 has to be 0, and V3 has to be 0. So you just end up with T 0, 0, which becomes a vector 1, 0, 0 if you pick T equals 1. Okay. Similar, when lambda is 2, you just go through the process, and I get -1, -1, 1. And so those are the eigenvalues. This matrix A is not defective. So A is 3 by 3. With 3 linearly independent eigenvectors. So A is not defective. Okay. Next problem. So here it says in exercises 23, we're finding a non-singular matrix P such that P inverse A, P is diagonal. So they are telling you to diagonalize A, okay? So maybe just a quick note here. This is just code for it says diagonalize A. I could have just said it like that. Okay, so P has this says eigenvectors for columns. Oops. Okay, and D is eigenvalues down the main diagonal, like this, with zeros everywhere else. Like that. Okay. So, and then P inverse is P inverse. So you can see this is actually a really easy one because this matrix is an upper triangular matrix and the determinant is just the product of the entries on the main diagonal. So even after you subtract lambda I minus A, you end up with an upper triangular matrix, lambda minus 2, lambda plus 1, lambda minus 3. You just multiply those to get the determinant, which is the characteristic polynomial. Set it equal to 0, and you've got your eigenvalues just as easy as it comes. Okay, once again, we're solving systems of equations. So we're just doing exactly what I've done on the last two examples. So with lambda equals 2, I put 2 in for lambda here and just row reduce, and I get an eigenvector where I picked t as 1. Okay, with lambda equals -1, same thing. A row always zeroes out. If it doesn't, you've made a mistake. Okay, once again, no fractions, so I pick t equals 1 and I get an eigenvector. With lambda equals 3, same thing. A row must zero out, but this time I ended up with fractions with 2 in the denominator. So obviously I picked t equals 2 to avoid any fractions. Okay, those eigenvectors become the columns here, 1, 0, 0, here, -1, 1, 0, and here, -5, 1, 2. Those are the eigenvectors in columns. Let me highlight that real quick.
I didn't get that. Could you try again?
No, you try again. Oh, gee whiz. Okay, so these are my eigenvectors here. And P inverse is what it is. D here, this diagonal matrix, these are the eigenvalues. So let's make that note down here. These are my E values. Okay. And if you multiply P inverse times AP, you will get the diagonal matrix D, which is to say that's diagonalizing A. It's just a change of basis matrix that gives us a new basis of eigenvectors, and the transformation relative to this change of basis is a diagonal matrix, which is the simplest kind of linear transformation. Okay, and that's why we do it, I guess. Next, let's do this one. This is just more. And they are saying these things in ways that are different, but it's still the same problem. So I tried to give you a clue on the previous problem that you're basically changing your basis to a basis of eigenvectors, and then the transformation matrix relative to the new basis is just the diagonal matrix with the eigenvalues down the main diagonal. Okay, so here's the transformation described this way, but you want to write this in column vectors and get the standard matrix here. Okay, and then I'm just going through the process of finding the lambda I minus A matrix, taking its determinant and hopefully factoring it and getting 3 eigenvalues or less. Okay, from those eigenvalues, you need to find 1 or more eigenvectors. They have to be linearly independent, okay, eigenvectors. And once you have those eigenvectors, hopefully without fractions, as long as you get 3 linearly independent ones, you can say, oh yes, this is a non-defective matrix, and the matrix is diagonalizable. Now, if you're trying to find a basis for the vector space such that the transformation relative to that basis has a diagonal matrix that represents it, then the basis needs to be a basis of eigenvectors. Okay, and this is the matrix for the transformation. I think the transformation was called T. Yeah, this is a matrix for T relative to beta. And it's a much simpler matrix than the one we started with. Okay, and if you want to do the transformation, just got this right here. If you want to do the linear transformation, T on any vector V relative to this new basis beta, it's super simple. You just multiply a given vector relative to beta by the diagonal matrix, which is the simplest way of expressing this linear transformation. Okay. Again, you're just diagonalizing a matrix. Next is a bit of a whopper. This is the one where you want to find an orthogonal matrix that whose transpose is equal to the matrix's inverse. So again, we're just diagonalizing, but the matrix is symmetric. And when the matrix is symmetric, I'm going to ask you to do it this way. Okay, first of all, it says to use a Gram-Schmidt process to orthonormalize the eigenvectors. So it's the same process in the beginning. Here, we take lambda I minus A and find its determinant. And I tried to be as careful as I could, factoring instead of multiplying, and this is what I got. Okay, now you can see that I get lambda equals -2 with a multiplicity of 2. So that's my first warning sign that the matrix might have been defective, except we have a guarantee that symmetric matrices are never defective. So I don't really have to worry about this. Now what that means is because the multiplicity is 2 here, it's guaranteed that 2 rows will zero out when you do your row reduction to find the eigenvectors. Okay, so the multiplicity of an eigenvalue is always the number of rows that zero out when you try to find the eigenvector. And the number of rows that zero out are the number of independent parameters in your solution, which gives the number of linearly independent eigenvectors. So when you put in lambda equals -2 into this lambda I minus A, you get this matrix. Every row is identical. So 2 of them zero out, and the top row just becomes 1, 1, 1. Okay, I get 2 independent parameters. Like the V2 and V3 columns don't have leading ones. So the V2 and V3 get to be S and T independently. V1 has to be -S minus T. Okay, and when I express my vector V, I write it this way, and I get 1, 2 independent eigenvectors here that are not orthogonal. Oops. Now, Gram-Schmidt does not affect the span of these 2 vectors. So if I apply Gram-Schmidt to these, they will still be in the same eigenspace, which means they'll still be eigenvectors. Okay, the first vector W1 gets to be V1, and W2 is going to be V2, but I'm going to subtract out the W1 component from it. So it will be orthogonal to W1. So that's what I'm doing here. You can see me multiplying by 2 just to scale it so that there are no fractions. I've got a 2 here because there's a 1/2 here, okay? And I can multiply this by any scalar I want as long as it's not 0, okay? And that'll give a vector that's still orthogonal to the first vector, and it will still be an eigenvector because it's still in the eigenspace. Remember, we can take any combination of these 2 vectors up here, and Gram-Schmidt says that when you orthogonalize them, they will still span the same space. And Gram-Schmidt is just taking linear combinations of these vectors. Okay, and this statement says any linear combination is fine. Okay, so now I end up with the two vectors. The first one's -1, 1, 0. The second one's -1, -1, 2. And these two guys are still orthogonal, are still eigenvectors, but they are now orthogonal. And you can check the dot product. Those will come out 0. So those are perpendicular. Now, when you plug in lambda equals 4 into the lambda I minus a system of equations, you'll get another vector. But because it comes out with just a TTT here, which is any multiple of 1, 1, 1, we are guaranteed that eigenvectors from different eigenvalues will be orthogonal automatically. So let's put that note up here. E vectors from different E values are automatically orthogonal. It just happens. You don't have to do anything to make those orthogonal. Okay, that'll just work out for you. Okay, so if you go and check this new vector that we got by putting in lambda equals 4, row reducing till the row zeroes out, which gives one independent vector here. Okay, this one comes out automatically orthogonal to the first two, which we made orthogonal to each other. And in the end, you'll have 3 orthogonal vectors. The next step is to divide them by divide each by its magnitude to make them orthonormal. Okay. Okay, so as I was saying, the dot product of any one of these with another will be 0 because they are orthogonal and we made it be that way. And then the dot product of any one of these with itself is always just the magnitude of that vector squared, but these are all unit vectors. So the magnitude squared is 1. So all of these dotted with themselves is a 1. All of them dotted with another is 0. And that's why when you take P transpose, okay, if you take P transpose and multiply by P, you're just dotting the rows of P with the columns of P transpose, which are again the rows of P. So you're dotting the rows of P with itself, and you're either getting 0s and 1s. And that's why when if you compute P transpose times P, this will be I, the identity matrix, because it's just full of 0s and 1s. Okay. And then if you multiply P transpose times AP, that's the diagonalization, P inverse times AP, that'll make the diagonal matrix of eigenvalues. So -2, -2, and 4, these are the eigenvals of A. So that's that. That's a lot of work. There's no way I can put this many eigenvector problems on the exam. Okay, now the last problem here says to prove that if A is similar to B and A is diagonalizable, then B is diagonalizable. So I had to think about this one for a little bit, but just a couple of definitions. If A is similar to B, then we know that A is equal to S inverse BS for some square matrix S. Okay. If A is diagonalizable, then A can be diagonalized. Basically, there's a matrix P that's full of eigenvectors for A, such that if you do P inverse AP, you'll get that diagonal matrix. Okay. So just observe that D, I set up above, is P inverse AP, but A above is S inverse BS. So I changed the A to the S inverse BS. I rearranged like this. Now, you may remember from a long time ago that P inverse S inverse is the same as SP inverse. You have to change the order on these to do that, which is really good because SP inverse here is the inverse of SP here. So why not just call that R or some other letter? So you end up with R inverse BR. And so what I've got here is that B can be multiplied in the front by R inverse and in the end by R, and you get a diagonal matrix up here. In fact, it's the same matrix that diagonalized A, which is another way of saying that A and B both have the same eigenvalues. Okay, so this proves that B is diagonalizable. Okay, that B has the same eigenvalues as A. And then I said something super complicated just to remind you that whatever this matrix is that you're multiplying A by, that P matrix there is the one that contains the eigenvectors for A. So when I see it down here, I see R inverse BR is equal to the diagonal matrix, which has the eigenvalues. And this R matrix, which was the S times P, that R matrix has to contain the eigenvectors for B. So that's all that I said down here. I believe that's the whole shooting match. So we're done. And like I said, if you guys have any questions, feel free to contact me during my office hours this week. Again, on Monday, it's 3:30 to 4:30, and on Wednesday, it's 9:30 a.m. to 10:30 a.m. So good luck on getting ready for your final next Friday at 7:30 a.m. I'll see you guys there. Bye.